Welcome to qnawire.
Hi, so for this question, we are using barbituric acid. I'm going to abbreviate it as BH for being an acid, and in order to write down the dissociation equations. And the concentration, it is going to be zero point 0.1 molar. We have 20 milliliters of this solution, and we are titrating with 0.2 molar NaOH. And here we're assuming that we have a one-to-one relationship in between the acid and NaOH. So for the first question is the initial pH of the solution. And in order to know that, what we need to do is take my barbituric acid in aqueous solution plus water, which is liquid and thus a pure substance. This is going to be in equilibrium with the associated anion in aqueous solution plus hydronium ion also in aqueous solution. Okay. So if we use our ice table, we know that the initial concentration of this acid is zero point 0.1 molar. Here, all of the values of the ice table is going to be in molar. And let's assume that we start with zero of each. Of water, it doesn't matter because it is a pure substance. Now, the amount of change, we're going to call it minus x. This is going to produce x and x over here. And at equilibrium, we are going to have zero point 0.1 minus x, x, and x. Now, if we look at the value for Ka, the Ka for this acid is 9.8 times 10 to the minus 5, then we know that that value, it is going to be generating a very small dissociation of the acid when it comes into water. So we can write down the Ka as the product of the concentrations of the anion, the concentration of hydronium that we are going to have, and the concentration of the acid. This is changing the values that we found from our ice table. This becomes x squared divided by 0.1 minus x. So now we can make an approximation and saying that 0.1 is much larger than x. Thus, 0.1 minus x is essentially zero point 0.1. We need to verify that this is true when we find our result. If the value for x that we find is larger than our assumption, then we would need to solve the full quadratic expression, meaning solving the equation that comes from this equality. Okay? So now, using the approximation, let's write down the value for Ka, that is 9.8 times 10 to the minus 5. We are going to multiply it. Well, first of all, rewriting this becomes x squared divided by 0 0.1. Solving for x, this is the square root of 0 0.1 times 9.8 times 10 to the minus 5, which is 3.13 times 10 to the minus 3 to the minus 3. So yeah, this was a good approximation because the value that we found of x is much smaller than 0 0.1, right? We are 2 orders of magnitude smaller in this scenario. So now let's recall from our ice table that that value for x was equal to the concentration of hydronium ion at equilibrium. So the pH it is going to be minus the logarithm of that x that we found. So that pH corresponds to 2.5. So this is our initial pH of our solution. That is answer A in your answer sheet and L answer sheet. So now for part B, which is your question 25, it asks you what is the pH after adding 5 milliliters of the solution. 5 milliliters of NaOH, 0.2 molar. Okay, so just by looking at the concentration, if the concentration of the acid that we have is 0.1 and we added 5 milliliters of a concentration that is twice, we know that we are going to be below the equivalence point. We can verify this by calculating the amount of mole that we have at the beginning of the acid. So, amount of mole of barbituric acid at the beginning, which is going to be the volume that we have of our solution, that is 20 milliliters. We are going to convert that to liters simply by multiplying by times 10 to the minus 3. And we are going to multiply this by the concentration, which is 0.1 molar. Okay. This is going to give us a value for 2 times 10 to the minus 3 mole of BH. This is going to be our initial amount. Now, let's calculate the amount of OH minus that we are adding. If we added 5 milliliters, this is 5 times 10 to the minus 3 liters, times the concentration of NaOH, that is going to be 0.2 molar. This is going to give us a 1 times 10 to the minus 3 mole of NaOH, or of OH minus directly, because this is a strong base, right? And one thing that you want to notice in this case is that you added exactly 1/2 of the amount of mole of the barbituric acid. That means that we are halfway through the equivalence point of our titration. And what happens when we are titrating a weak acid with a strong base and we're in the halfway point? We know that the pH, it is going to be equal to the pKa of our acid. In this case, the pKa of the acid is minus logarithm of 9.8 times 10 to the minus 5. So the pH is going to be 4. Okay. Just to convince you of that, let's do again the ice table with these quantities. In this case, we are not going to require this is going to produce B minus plus water. In this case, we are not going to require to convert to concentrations directly because everything is going to be in the same final volume, but we can do it regardless. In this case, let's stick with mole because we already did the calculation in mole. Remember that converting to concentrations, it is going to become important when we want to calculate the pH. Okay. So in this case, in moles, what we have is 2 times 10 to the minus 3 of OH minus. I have 1 times 10 to the minus 3. The amount of change, it is going to be the same as the limiting reagent, that is OH minus. So at equilibrium, I'm going to have 1 times 10 to the minus 3, approximately 0, and 1 times 10 to the minus 3. And guess what? We have the combination of an acid and conjugate base, which in this case, it is going to be a buffer. If you want to convert all of these quantities into if you want to convert all of these quantities into concentrations, you could divide all of these things here by the final volume. In this scenario, since we have a one-to-one correspondence and the final volume is going to be the same always, it really doesn't matter. But realizing that we have a buffer, we know that the pH is going to be equal to pKa plus the logarithm of the concentration of the conjugate base divided by the concentration of the acid. This is going to be logarithm of 1 times 10 to the minus 3 mole divided by final volume divided by 1 times 10 to the minus 3 divided by final volume. This is pKa plus logarithm of 1. Logarithm of 1 is 0, so pH is pKa. And as we mentioned, that corresponds to equal 4, as we did our calculation at the start of this section. And that would be all. Well, it would be 4.0 something, but essentially 4 for our scenario. And that would be all.